Now we're moving on to the topic that is going to take up most of this class, electricity, and later we'll talk about its relationship with magnetism. Up until this point, the units that we've used in physics, or the quantities that we've used in physics, you've been able to make them out of the fundamental units of time, mass, and distance. And everything has been made out of that. Like units of force are distance divided by time squared times the mass. So you can make all these things like newtons are made out of all these just these fundamental things. But now with electricity, we're going to introduce a new quantity that we haven't seen before, and you can't make it out of time and distance and mass. Electricity introduces a fundamentally new quantity and that quantity is charge. One thing about charge is it's conserved. Charge isn't created or destroyed. So total charge always stays the same. And the SI unit for charge is called the coulomb. It's abbreviated with a capital C. And one thing about charge, one thing about this unit of coulombs, it's a very big unit compared to our sort of experience with electricity. So to get a sense of how big a coulomb is, you probably know that opposite charges attract each other, like charges repel each other. So what kind of force, if you had two 1 coulomb charged particles, okay, so each of those is 1 coulomb, and you had them separated by 1 meter, so they're 1 meter apart, what kind of repulsive force would they apply to each other? And you'll see this when I introduce the equation from Coulomb's law. But the answer is almost 10 billion newtons of force. Okay, so, I mean, enough to rip anything you're used to dealing with to shreds without even noticing it. So that's how big a unit of a coulomb is. So when you see charges in this class, you're usually going to see charges that are, way, way less than 1. Charges originate in atoms, and an atom is sort of structured like this. This is the nucleus of the atom, and then there's a surrounding of the nucleus. And the nucleus is made up of protons and neutrons. And then around the nucleus are electrons. And most charges have to do with motion of electrons. So electrons and protons, electrons are negative, protons are positive, but they have the same magnitude of charge. So an electron, a single electron has a charge of negative 1.602 times 10 to the minus 19th coulombs. A proton has a charge equal and opposite to that, so 1.602 times 10 to the negative 19 coulombs. That's just such a tiny fraction of a coulomb. One other thing that is worth noting is even though these have equal and opposite charges, the masses are very different. A proton has about 2,000 times the mass of an electron. And then a neutron, comes from neutral, has zero charge, and it has the same mass as a proton. Okay, the calculations that we're going to do are going to just relate to this repulsion and attraction. So if you have like charges, they repel each other. And if you have opposite charges, they attract each other. And the calculations we're going to do are all going to relate to these repulsion or attraction. And so in talking about these, this repulsion and attraction, we could use the ideas that we have before. I mean, we'd have to introduce charges into it, but we could think about these in terms of force, potential energy, and work. I mean, they're pushing each other apart or attracting each other towards each other with forces, and you can talk about sort of the relationship between forces and positions in terms of potential energy. You could do that, but with electricity, it tends to be more convenient. It is more convenient, and people take advantage of that convenience to talk about them in terms of slightly modified things. So it's more convenient to use these new ideas, and those are the electric field vectors and electric potential. Electric field vectors we're going to use for a lot of calculations, but those don't relate to anything that in your daily life you deal with. But electric potential is something that you're very familiar with, at least you've heard about many times. A difference in electric potential between 2 points. So the difference between two electric potentials is the voltage. And voltage is going to be an important idea in talking about electricity. Okay, so what's the definition of these things? The electric field vectors have a relationship with force where the force vector is equal to the electric field vector times the charge of the particle. And so if you know the force vector that an object feels and you divide it by the object's charge, you get the electric field vector. And similarly, the electric potential is related to potential energy, where the potential energy is the electric potential times the object's charge. So basically, the difference between these quantities that we're used to, force and potential energy, and these new quantities, electric field vector and electric potential, just have to do with multiplying or dividing the charge of the particle that you're dealing with. One other thing to remember about electric potential is, about electric field vectors and electric potential, is in the last class, the Physics 1 class, one of our main derivative relationships said that the force on an object is equal to the negative derivative with respect to x of the potential energy. And based on this relationship and based on how similar electric field vectors and electric potential are to force and potential energy, you'd expect a similar relationship between electric field vector and electric potential. And we will see that. I'm going to start by talking about the electric field. And a field is a way to talk about conservative forces. Remember, conservative forces are forces where if you know the object's location, then you know the force that's applied to it. And the ones we've dealt with so far up until now are gravity and spring forces. Well, the idea of a field is that you can think, since the location is associated with a certain force, you can think of a force waiting in space for the object to get there and kind of activate this force. And I think the visual there is, imagine a field of dandelions or whatever. If you walk in a field of dandelions, if you go over to this location, there's a dandelion there for you. If you walk to this location, there's a different dandelion waiting for you. With an electric field, you can go to these different locations, and rather than a dandelion waiting for you, there's an electric field vector, which isn't as fun to blow or whatever, but it's helpful in doing electricity calculations. So remember that the electric field vector is related to force. And the relationship says that the force vector is equal to the electric field vector times the charge of the particle that you're thinking of. The SI units for electric field vector are, well, you can figure it out from this equation. It's going to be newtons divided by charge, so newtons per coulomb. And for now, the only calculation that you're going to need to do to figure out the electric field is to calculate the electric field vector due to a fixed charge in space. And the equation for that is that the magnitude of the electric field vector, that's why I'm not putting a vector sign on this, this is just a magnitude, is equal to 8.99 times 10 to the ninth. I'm going to leave the units off to make this look cleaner, but this is in SI units, times the absolute value of the fixed charge divided by r squared, where r is the distance from the fixed charge to the point where you're trying to calculate this. Okay, so there's a fixed charge in space that lays out this field, and then you're calculating the electric field vector at your chosen location. Okay. So r is the distance from the fixed charge to the point where you're calculating that E value. Now, I gave you this calculation. Let me tell you what Q is here. So Q is the charge of the fixed charge that's creating the electric field. Now, the last thing we have to talk about is I've only given you a way to calculate the magnitude of that force. A vector has to have a direction in addition to the magnitude. So to figure out the direction, you just have to remember that this is toward the fixed charge if that fixed charge is negative. And away from the fixed charge if the fixed charge is positive. Intuitively, the way you can think about this is the direction of the electric field vector is going to be the same direction as if at your location where you're doing this calculation, you had a positive charge. Okay, so you can always just think of moving a positive charge around. What's the direction of force that the fixed charge would apply to it? Now, what would you do if you had 5 charges and you wanted to figure out the electric field due to all 5 of these fixed charges? Could you do that? Yeah, actually, it's really easy to do. You just calculate the electric field vector due to each one of those forces individually, and then you add them up to figure out the electric field vector, the total electric field vector at that point. So I'm going to do an example like that. Okay, so let's say that we have a setup like this. We have a fixed charge at location 1 and a fixed charge at location 2. And then we have this point in space where we're trying to do a calculation. I'm going to call this point P. And I got to give some geometry stuff. So let's say that each of these 2 angles is 75 degrees. those add up to 150, so we know that this one has to be 30 degrees. And let's say that the distance between these two fixed charges is 1 times 10 to the minus 4 meters. So they're very close together. And the charge at 1, we're going to say is positive. So this, let's call this positive 1 times 10 to the minus 8 coulombs. And the charge of the second one is negative 2 times 10 to the minus 8 coulombs. So this second charge, fixed charge, has twice the magnitude of the first fixed charge, and they're in opposite, they have opposite signs. So you could think of the charge number 1 is made of protons, charge number 2 is made of electrons. And we want to calculate the electric field vector at the point P. And then we want to use that electric field vector to calculate if there was an electron at that point P, what's the total force applied by those two fixed charges? Okay, so our strategy here is we're going to first calculate, we're going to forget about this fixed charge number 2, and we're going to calculate the electric field vector due to the fixed charge 1. Then we're going to forget about 1, calculate the electric field vector due to the fixed charge 2, and then we're just going to add them together, and that'll give us our total electric field vector. So we got to do some geometry here. So let me redraw this triangle. And I'm going to make this a right triangle so we can use sine and cosine and tangent. That means that this angle is 15 degrees. This angle is still 75 degrees. This distance is half of the distance between fixed charges 1 and 2. So this is 0.5 times 10 to the minus 4. And we're going to use these values to figure out the length of one of these diagonals. Because this is a isosceles triangle, those two diagonal lengths have to be the same, so we only have to calculate it once. Okay, so we'll think about this right triangle. And I'm going to use this 15 degrees, and I'm going to use 0.5 times 10 to the minus 4. And we want to calculate this length L. Well, SOHCAHTOA says that the sine of 15 degrees is equal to the opposite to that 15 divided by the hypotenuse. And so the hypotenuse is 1.932 times 10 to the minus 4 meters. What do we need that length for? We're going to need that because that's going to be the r that goes into our calculation of the electric field vector. Okay, so the magnitude of the electric field vector due to the fixed charge of 1, remember we're ignoring the one at 2 for now, is equal to 8.99 times 10 to the 9th times the absolute value of this fixed charge at 1. So that's 1 times 10 to the minus 8th. And then divided by that length squared that we just calculated. That's the distance between the fixed charge at 1 and the point where we're doing this calculation, P. So 1.932 times 10 to the minus 4th, and then you square that. That's what the formula says. And you get a value of 2.408 times 10 to the 9th newtons per coulomb. Now we have to think about the direction of that. Okay, so remember that the rule for the direction of electric field vectors is it points away from positive fixed charges and toward negative fixed charges. This fixed charge is positive, so it's going to be pointing exactly away from it. And so that is this direction, okay? Like if you think of this field vector happening at the point P and just draw an arrow exactly away from a positive charge, okay? Well, the last thing we have left to do then is to come up with vector components for that. So to come up with vector components, we're looking for the lengths of these two legs. Okay, I'll call this Lx and this Ly. Those are what we're trying to find. And we know now that the length of the hypotenuse is 2.408 times 10 to the 9th. And we know that this angle is 15 degrees. And so use SOHCAHTOA again. We know that sine of 15 degrees is equal to Lx over 2.408 times 10 to the 9th. Solve for Lx. And it's 2.408 times 10 to the 9th times the sine of 15. And so you get 6.232 times 10 to the 8th. And now to think whether that's positive or negative, think about, is this hypotenuse, the vector, less than 90 degrees or greater than 90 degrees from the positive x-axis? Okay, well, we know, I mean, we've actually drawn it here, that if the positive x-axis is going to the right, our vector is 75 degrees from that. And so since this E vector is within 90 degrees of the positive x-axis, the x component is positive. Okay, so the x component is positive 6.232 times 10 to the 8th newtons per coulomb. And now what about Ly? Well, we know that the cosine of 15 degrees is equal to the adjacent over the hypotenuse. So it's equal to Ly over 2.408 times 10 to the 9th. And you get, for that, 2.326 times 10 to the 9th. Now we have to think, is this E vector within 90 degrees or more than 90 degrees from the positive y-axis? It's less than 90 degrees. It's close to the same direction as the positive y-axis. And so that says that the y component is also positive. And so now we can put it all together. The electric field vector due to the fixed charge at 1 is positive 6.232 times 10 to the 8 newtons per coulomb in the I direction, the positive x direction, plus, guess I don't need that, 2.326 times 10 to the 9 newtons per coulomb in the j direction. Now we have to do the same thing for the other fixed charge. We've figured out the electric field vector at P just due to 1. Now we have to figure out the electric field vector at P just due to 2. Okay, so the magnitude of the electric field vector due to 2 is 8.99 times 10 to the 9th times the absolute value of that fixed charge at 2, which in this case is 2 times 10 to the minus 8th. Now, this is really important. We're just looking for an absolute value of that charge. So our fixed charge at 2 is negative, but we're not dealing with that yet. We're putting it in as positive and then dividing by the distance between P and the fixed charge 2 squared. So that's 1.932 times 10 to the minus 4th squared. And you get a magnitude of 4.816 times 10 to the 9th newtons per coulomb. Now that we have the magnitude, we can think about the direction. So let's go back to our starting picture. This time, the fixed charge is negative. And so if you think about a vector originating at this point P, that vector is going to point toward the fixed charge at 2. So this time, the direction is this way. And now we have to figure out the components like we did before. So here is our vector that has a magnitude of 4.816 times 10 to the 9th. Here are the components we're trying to figure out. This is 15 degrees, and I'll call this Lx and Ly. And we'll use SOHCAHTOA again. The sine of 15 degrees is equal to the opposite over the hypotenuse. And so Lx is equal to 1.246 times 10 to the 9th. The hypotenuse, that vector, is within 90 degrees of the positive x-axis. Which means that that component is positive. And now we have to calculate Ly, the cosine of 15 degrees is equal to the adjacent over the hypotenuse. And so Ly is equal to 4.652 times 10 to the 9th newtons per coulomb. This time, notice that this electric field vector is greater than 90 degrees from the positive y-axis. You know, the positive y-axis is this. The electric field vector is this. That angle is more than 90 degrees. So it's over 90 degrees from the positive y-axis, which means that the y component is negative. And so finally we can write down our components for the electric field vector due to the fixed charge at 2. And this is 1.246 times 10 to the 9th newtons per coulomb I. And now here's where the negative comes in for the y component, minus 1.869 times 10 to the 9th newtons per coulomb times J. Not quite done. Now we just have to add these two things together. So the total electric field vector is the electric field vector due to the fixed charge at 1 plus the electric field vector due to the fixed charge at 2. That just means adding up the I stuff, and that's your I component, and adding up the J stuff, and that's your J component. So this comes out to be 1.869 times 10 to the 9th newtons per coulomb I minus 2.326 times 10 to the 9th newtons per coulomb J. And if you wanted to visualize what the vector that those components form, you could draw the coordinate axes, plot out that point. So let's say it goes over in the positive x direction this way. You know, think of these as the coordinates of a point. And so it would be something like this. Then make that the head of your vector with the tail at the origin. And it's sort of in that direction. Okay, the part B, now this is going to be quick. The part A is pretty long. So now part B, it says, okay, now don't just think of that point P as a location. Think of there being a charged particle there, and let's calculate the force on that charged particle. We said that the particle we're going to put at P is an electron. So the lowercase q, hold on. So the lowercase q in this case is the charge of the electron, which is negative 1.602 times 10 to the negative 19 coulombs. So multiply that to each component of the electric field vector, and you get a force vector of negative 2.99 times 10 to the minus 10th newtons in the I direction, plus 3.726 times 10 to the minus 10 newtons in the J direction. Okay, obviously that's a pretty involved calculation, but that's the only kind of calculation you're going to have to do with these electric fields to get these electric fields. There is one other type of electric field that you'll have to deal with, but that calculation is trivial. So one other important type of electric field and that is charged parallel plates. Okay, so like an example of this would be you have a positive charge on one of these plates, a negative charge on the other plate. And if the height of these plates is bigger than the distance between the plates, so think of this distance d, and this is the height. So if the height is bigger than the distance, then there's a uniform electric field in between the two plates. Which means everywhere between the two plates, the electric field is the same. And it always goes from the positively charged plate to the negatively charged plate, so that's the direction. And the magnitude of it is the charge divided by the area of one of those plates divided by the constant 8.85 times 10 to the negative 12. And that's in SI units. Okay, so the way that it's drawn here, these electric field vectors are always going to go to, all of them are going to go to the right. If, on the other hand, the right plate was positive and the left plate was negative, these electric field vectors would point to the left. It always goes from the positive to the negative.